My name is Drew Griffiths, and this is my presentation on Lab 3 Black Holes for Physics 2211. So this lab has two parts. The purpose of the first part is to analyze a star's motion to find the mass of a black hole acting on it. And secondly, we're supposed to use the mass of that black hole to calculate the initial velocity of a spaceship to get it as close to the black hole as possible without getting sucked in or crashing to the planet that is also orbiting the black hole. So here are the physical principles and the formulas that I used during this lab. So I used Newton's second law, which says that F net is equal to the derivative of momentum over the derivative of the change in time. And also use the gravitational force equation, which is that F grav equals the gravitational constant times the mass of the two objects times r hat, which is the direction vector of r, and then the magnitude of r squared divided by that. And then I also use the velocity update formula and the position update formula that we have used in previous labs also. So here is my GlowScript model for part 1 of this lab. So on the left here, I set the seed and the initial constants for this lab, which is changing the mass of the star and changing delta t. And then on the right here, there's some computational steps that I had to go through to calculate the mass of the black hole. And the mass of the black hole is calculated using this equation at the bottom here, which is rearranging the force of gravitation equation that I showed in the earlier slide. Are my results for part 1 of the lab. The mass of the black hole I calculated to be 8.385 times 10 to the 33rd kilograms, and I calculated this by finding the average of all of the results that the computational model gave me, because they gave me many numbers, and we only need one answer for the mass of the black hole, so I just averaged them. Then F net is equal to 7.98 times 10 to the 28th kilograms. The parallel component of the net force is 2.2 times 10 to the 20th kilograms, and the perpendicular component is 7.65 times 10 to the 28th kilograms. And here is my GlowScript model for part 2 of this lab. And on the left here, the only initial condition I changed was I imported the mass of the black hole. And then on the bottom left here, these velocities, the initial velocities for the ship, were found using trial and error by just running the model and trying different velocities to see which one got the spaceship closest to the black hole without getting sucked in or crashing into the planet. Then over here on the right is the computational steps that I used to calculate this. And each one, the F net from the black hole on the planet, F net of the planet, that's all calculated by using the gravitational force equation from earlier, the G m times r hat divided by the magnitude of r squared. And that's the equation I used to calculate all of these. Now they're at the bottom. This is where I use the position and velocity update formulas to update position of the velocity, to update the velocity of the planet and the position of the planet, and the same for the ship as it travels around the black hole. And here you can see are my results. So here in pink, that's the spaceship. I try to get it as close as possible without crashing or getting sucked into the black hole. And as you can see, the plane is also orbiting the black hole, the plane that's in blue. And some possible errors for this lab is that the results are found using approximations, as the computational model can be completely accurate. It rounds or truncates. And also the initial velocity of the ship, that was not completely accurate, as it was found using trial and error, as I was trying to get as close to the black hole as possible. But it likely could have been a little bit more accurate, but if I didn't use trial and error. Here are the discussion questions for my lab. What is the difference between the net force and the rate of change of momentum? These are actually the same. They're equivalent using Newton's second law. It states that the net force is equal to the change of momentum over the change in time. So these two are both mathematically equal or equivalent, but it's easier to calculate the change of momentum rather than the net force, because instead of calculating each force and their components, you just have to calculate change of momentum, which can be found the mass times change of velocity over the change in time. And then what if I wanted to get the spaceship to enter orbit? what initial velocities for the ship would I have to use. And I did trial and error as well for this one. And I came up with that the velocity in the x direction should be -1 times 10 to the sixth, and the initial velocity in the y direction should be 8 times 10 to the sixth. And that's it. Thank you for watching my lab.